The next method we're going to talk about here isn't really a method on its own, but it's more just an extension of the disk method. It's referred to the washer method, but it is just the disk method. But it's an extension of the disk method, allowing you to find the volume of a rotated region when that region is not fully connected to the axis of rotation. Let me explain what I mean there. So, for instance, let's say I have the region here in this first picture, and I want to rotate this region around an axis. If I were rotating around this axis right here, so where y is equal to 1, then this region, the blue shaded region that I've colored in, is entirely connected to my axis of rotation. So every single point in this region connects to my axis. But that's not always the case. So for instance, if I were to switch and make this rotating around the x-axis, well, now there's this gap right through here where my region is not connected to the axis of rotation. And so the washer method allows you to go ahead and rotate this non-connected region around the axis without any issues. So the way it does it is actually very similar to how we did the area between two curves. In fact, the formula for the washer method, if you notice right up here, the formula for the washer method is the volume of this region is pi times the integral from a to b of an outer radius squared minus an inner radius squared integrated with respect to x, or of course this could be integrated with respect to y, just depending if you want to use an axis that is vertical of rotation or an axis that is horizontal, so just depending on the rectangles that you choose in your approximation. But if you'll notice, this is really just the exact same thing. Like if I distribute this pi, I would have the integral from a to b of pi times this outer radius squared. And since I have two parts to my integral, I can actually split this integral up and separate it. So this is really minus the integral from a to b of pi times the inner radius squared dx. And each one of those separately is an integral that calculates, because it's pi times a radius squared dx, that's going to be integrating using the disk method. So we're just doing the disk method for the outer region and then doing the disk method for the inner region and subtracting the results. So it's exactly the same thing as the area between two curves. Okay, now to see how this works, let me show you real quick here through this small little illustration that's provided by our publisher. So you draw your curves. Generally there's going to be two curves involved at least, and you will set up your approximating rectangle. All right, so they've drawn in their first approximating rectangle here. All right, so you have this rectangle between your curves defining basically the top of the rectangle, or in fact we should probably think in terms of the most positive part. And then of course the bottom of the rectangle, or better yet, the most negative part. Okay, because you want to set up these so that you get a positive value when you rotate, so that you get a positive volume when you calculate in the end. Okay, so then you'll take that one rectangle, you rotate it around the axis. All right, and I'll probably ruin this picture that they've drawn here, which is so nice to start with. But essentially what it will do is produce this region that has a hole in it. Okay, that's what I'm trying to illustrate here. But there's a hole in this region because you have the outer radius minus the inner radius. It leaves a sort of a disk, but a disk with a hole in it, which is called a washer. Okay. Then, when you take the region completely between two curves, so you take the entire region now, and you rotate that around your axis, and in this case we are rotating around the x-axis here, then what happens is you get this solid region, but with a hole missing in the middle. So there is a region in the center that is missing. So that's how we get the volume of an object like this. So let's take a look at how we actually work through one of these problems. So our first example here, find the volume of a solid of revolution formed by revolving the region bounded by the graphs of f of x equals the square root of x and g of x equals 1 over x over the interval 1 to 3 around the x-axis. Okay, so first things first is we need to get a picture of our region. That's always the best place to begin. Some students I see will try and just start throwing things into formulas and by intuition, and that will work a lot of times, but not necessarily always. It depends on how familiar you are with the curves. Sometimes on the interval from 0 to 1, it's a little bit surprising which functions are actually larger than other functions, just, you know, how decimal multiplication works and that sort of thing. So it's really best to just get some pictures and go from there. Okay, the square root of x. So that is going to have this kind of shape right here. I don't need to be terribly accurate with it. I'll just do my best there. That's fine. And then 1 over x in just quadrant 1, of course, we have horizontal and vertical asymptotes. I'm not really going to be concerned with those. I'm just going to draw in the basic shape. It would pass through this point 1, 1, and then just sort of go like that. All right, so that's what the function g will look like within the first quadrant. All right, now it did tell me that my region was bounded between x equals 1 and x equals 3. Now remember, this, even though it wasn't said that this is an interval of x, because the functions are of x, that defines this to be an interval of x. All right, and then lastly, I am going to rotate all of this around the x-axis. Okay, so I have my region. That's easy enough to see right through there. Shade it in here real quick. Okay, now since I'm rotating around the x-axis, I will need to use a vertical rectangle. I don't really have any choice here because, again, even with the washer method, we don't have any means of dealing with rectangles that are oriented perpendicular to the axis of rotation just yet. So that's how we'll need to start. Now, the way that this will work, we have to set this up so that we'll get a positive answer in the end. So since this is our axis of rotation, you'll decide on what's the inner radius and the outer radius depending on which is further away from the axis of rotation. It's not necessarily like which is most positive in every single scenario. It just depends on which is furthest away. So this right here is going to be my inner radius because it's closest to the axis of rotation. And this right here is going to be my outer radius because it's furthest away. So the outer radius is f, and the inner radius is the function g on this entire interval. Okay, so that pretty much gets us set up. The volume here, pi times the integral. We're integrating from 1 to 3 on the x, and we are still doing this dx because we have a vertical rectangle. And then, of course, it is the outer radius squared minus the inner radius squared dx. Okay, so then this becomes the integral from 1 to 3. I decided that my outer radius was the function f, which is the square root of x. And then my inner radius is the function g, which is 1 over x. And I am still going to use f in int, but I think I'm going to do just a little bit of simplification before I jump into that. And we'll make this square root of x squared becomes just x, and this would be 1 over x squared, just to make it easier to type into the calculator. All right, so math 9, this is the integral from 1 to 3 of x minus 1 divided by x squared. Oh, shoot. Try that again. And then that integrates dx. All right, so I get basically 3 1/3. Let's go ahead and change that into a fraction, so that's 10/3, but then it's still multiplied by pi, so this would be 10 pi over 3 as a final answer.